This is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And in today's topic, we will see the problems on elliptic, hyperbolic, and elliptic parabolic equations. So, in the previous sessions, we have seen the classification of PD. We'll just recall for a few minutes so that we can solve numerical problems on this topic. Okay, so we had seen partial differential equation. So basically, we have differentiated what is PD and ODE. So we have seen what is difference between dou by dou x and d by dx actually. So when I say it is dou by dou x, when I use dou by dou x, so the dependent variable. So basically, this is called dependent variable, and the denominator term, this is called independent variable. So the dependent variable, if it is, let's say the phi dependent variable is depending on, let's say, more than one independent parameter, which is called x comma y comma z comma t, so on, something like that. So this is the phi, the dependent variable is depending on more than one parameter. So therefore, it has to be evaluated with the partial differential equation. So when you have only, let's say, phi of x, okay, or phi of y, okay. So if the dependent variable is depending on only one independent variable, which is either on x, on y, on z, so then we use d by dx. So that is the difference. So here we write a second order partial differential equation. So where you have the first term dou square phi by dou x square. The second term is called the mixed derivative, which is dou square phi by dou x dou y. So the third term, which is dou square phi by dou y square, and the fourth term we have dou phi dou x. Fifth term dou phi dou y, and the constant phi plus g constant is equal to 0. So what we have done in the second step, so we have taken all the first derivatives in the right hand side term such that so we have this second order PD equation here on the left side. So this second order PD equation, so we are classifying in different terminology using Cramer's rule. So we had seen already. So again we had taken the chain rule for the phi of x. So the phi of x in the sense, so which is dou phi by dou x. Okay. So phi of y is nothing but so that will be dou phi by dou y. So for this we are taking the chain rule. So the exact differential of phi of x and exact differential of phi of y. So when we apply chain rule, so here we have two terms, okay, which is of mixed derivative and which is of dou square phi by dou x square. And similarly, when we apply the chain rule for this exact differential, same we have mixed derivative term and we have dou square phi by dou x. Now we have equation 1, so which is having all three parameters, which is second order derivative in terms of x, second order derivative which is mixed derivative, second order derivative with respect to y. And here in the second equation also we have second order derivative which is mixed and with respect to x, and in the third equation we have second order derivative which is mixed and with respect to y. So we will take these three equations and we will frame a coefficient matrix and we will follow the Cramer's rule to find out the value of mixed derivative. So here you can see the mixed derivatives value can be found out using Cramer's method actually. So recalling again, so let us consider equations to see again how Cramer's rule will work. So A1, let's say x plus B1 y plus C1 z is equal to D1. Next A2 x plus B2 y plus C2 z is equal to D2. Next A3 x plus B3 y plus C3 z is equal to D3. So let's apply the Cramer's rule for these three linear equations. So how do we get? First, let's form the coefficient matrix which is called A of these all linear equations. So how many linear equations we have? We have three linear equations. For these three linear equations, let us see. So what is the coefficient matrix A? So A is nothing but we have A1, we have A2, so we have A3. So here we have B1, we have B2, and we have B3. So here we have C1, C2, and C3. So this is nothing but the coefficient matrix A. So next, the constant matrix, let us take that is B. So which is nothing but D1, D2, and D3. So basically this is called the constant matrix, and the x column vector, so we call x is equal to, so we have x, y, and z. So this one we can write in the form of ax is equal to b. Fine. So here, if you want to find the value of x, so what we do? So we will replace the value of B matrix in the first column of the A matrix. So basically B is a column vector. So this column vector which has three rows, like one column. So here it is 3 cross 3. So here it is 3 cross 1. Okay. So what we do to find, let's say we want to find the value of y. So how do we get is y is equal to, so det of, so what we do, so we have to replace this second column by this B matrix. So what we get, A1, A2, A3. Here we have D1, D2, D3. So here we have C1, C2, C3. So divided by the det of A. Okay, so this is how we find the values using Cramer's rule. So if you want to find the value of, let's say, x, so this is the first value, then what we do, so we will take this B matrix and substitute in the first column. And let's say if you want to find the value of z, so what we do, so we will actually take this B matrix and substitute in third column. So this is how basically we get the values of x, y, and z correspondingly with Cramer's rule. Okay, so this concept is applied for these three equations. So we have equation 1, so which is of a into dou square phi by dou x square plus b into dou square phi by dou x dou y plus c into dou square phi by dou y square. So this is the first equation we have, and the second equation, so we have dou square phi by dou x square into dx plus dou square phi by dou x dou y into dy. So the third equation, like we have dou square phi by dou y dou x into dx plus dou square phi by dou y square into dy. So these three equations, so we will get what is the coefficient matrix A and the x matrix and the B matrix. Okay. So here the x matrix will be, so what it will be, so we have three terms, so which is dou square phi by dou x square, so we have one, and dou square phi by dou x dou y, we have second one, and dou square phi by dou y square, which is third one actually. So this is the x matrix. Fine. So these are the x matrix, so or the variable values which we need to find. So here we are finding those the mixed derivative term. So for the mixed derivative term, what we have done? So for the A matrix, so whatever the B column vector is there, we are replacing in the second column, and we have replaced it. And in the denominator, we can see A, B, C. So which is the first equation coefficients, dx, dy 0, which is the second equation coefficient. So here I will write. So basically you'll get to know. So what is the x matrix? So dou square phi by dou x square and dou square phi by dou x dou y and dou square phi by dou y square. Okay. So here, if you multiply with this one, you'll get the first equation. If you multiply this row with this column, we'll get the second equation. If you multiply this row with this column, we'll get the third equation. So this is how we perform Cramer's rule. Now using this Cramer's rule, so if this det is equal to 0, so what happens actually? So this will be infinite actually. So the det will not, if we make it 0, so what happens? What are the possibilities we will see? So when you make det equal to 0, so we will get so the discriminant value. So the equations in the form of, so a into, so dou square y by dou x square plus b into dou y by dou x plus c is equal to 0. So we'll get in this form. So when you apply the Cramer's rule and when you rearrange, sorry, when you make that is equal to 0 and when you rearrange equation, we'll get in this. So when it is like a second order equation, okay. So for this, if you want to find roots, so we have a formulation, so where we can get it as so let's say dy by dx of 1 comma 2 is equal to, so minus b plus or minus under root of b square minus 4ac divided by 2a. So this is what we have. So this concept we are utilizing here, and seeing the value b square, the b square minus 4ac. So this b square minus 4ac value, if it is less than 0, we have seen that it is elliptic equation. And if this b square minus 4ac value is equal to 0, so we have seen this as parabolic equation. And if this b square minus 4ac value is greater than 0, so we have seen that it is hyperbolic equation. So we have these three forms of equation. Okay, and then now after that, so let's do some sample example problems for the equations. So here you can see u of xx plus x square into u of yy is equal to 0. So basically the meaning of u of xx is, so dou square u by dou x square. So it is differentiating the value of u twice with respect to x. So that is the meaning of, so u of xx. Okay. So what is u of yy? So u of yy is nothing but, so dou square u by dou y square. So then what will be the corresponding equation? So we have dou square u by dou x square plus x square into dou square u by dou y square is equal to 0. So we need to see, so basically whether it is forming an elliptic equation or not. So here it is given at x is equal to 0, what happens also we need to find. Okay, so let's do it. Okay, now what happens actually? So the value of a here, this is 1. Okay, so b is 0. Why? Because when you take the second order equation, so what we have, so a into, so dou square 5 by dou x square plus b into dou square 5 by dou x dou y plus c into dou square 5 by dou y square is equal to 0. Let's take this. So here you compare this equation with this. So you compare this equation with this. So here what happens? So this term, let's say, is equal to the first term. So what is the value of a here? A is nothing but 1. And in this equation, so we don't have any mixed derivative term. So we don't have any dou x dou y term. So here we don't have dou x dou y term. So if you have dou x dou y term, so additionally you will have in terms of like this u of x comma y, let's say. So if you have in this way, so then you can assume that you have mixed derivative term. So since we don't have any mixed derivative term, the value of b is 0. And so C, so basically the value of C is equivalent to x square. So here it is written. Okay, so the discriminant, so which is b square minus 4ac. Okay, and if we calculate, so what happens actually, so a is equal to 1 and b is equal to 0 and c is equal to x, so x square. So basically what happens, so this becomes 0, so minus 4 into 1 into x square, which is become minus 4 x square, so which has come less than 0. So for x value, all the values of x, let's say except at 0. So at 0 what happens, it is neither, like it is not less than 0. Okay, so whatever the value of x you take, either you take minus 1. So when you have the value of 4x square, you take x is equal to minus 1, it will be 4x square. You take x is equal to plus 1, it will be again minus 4, sorry, minus 4 only. So you take negative values of x or you take positive values of x, so this value is unaffected. So therefore what happens actually, the discriminant value is less than 0. So here what we have concluded, so if the discriminant value is less than 0, it is elliptic. Okay, so now, so it has become elliptic. So when it has become elliptic, so let us calculate, let's see, so what are its roots. So lambda 1, so which is b minus, so this I is nothing but your complex number, so under root of 4ac minus b square divided by 2a, so which has come as minus ix. Okay, this is the first root. Next, second root, so b plus I into I into under root of 4ac minus b square divided by 2a. So here what is the value of a? 1, b is 0 and c is x square. So it has become ix. Okay, so lambda 1 is nothing but we have dy by dx. Come on, lambda 2 is nothing but, so this is our first root. So lambda 2 is nothing but dy by dx, that is for second root. Okay, so this is the first equation, this is the second equation. So these equations, okay, they are called the characteristic equations. Okay, so these characteristic equations, when you integrate, so you will get in this formulation. Okay, so these are the equations corresponding for the elliptic equations. So when you perform this discriminant and get the characteristic equations. Okay, so this is what we have. Next, so let's see the trigonometry equation. So trigonometry equation, so basically it's somewhat tricky. So here you can see, so when value of x is greater than 0, so basically it has come as hyperbolic. If is equal to 0, it has come to parabolic, and if it is less than 0, it has come to elliptic. So basically this equation is somewhat tricky, so depends on the value of x. So here you can see u of xx minus x of u of yy is equal to 0. So let's take, so let us do it in the rough sheet here. So we have u of xx minus u of, sorry, of x into u of yy is equal to 0. Okay, so let's work it out here. So what is the, let's take x is greater than 0. So let us assume, so the value of x is 2. Okay, so plus 2. Now what happens? So u of xx minus 2 u of yy is equal to 0. Then what happens actually? So dou square u by dou x square minus 2 into dou square u by dou y square is equal to 0. Okay, so this is what we have. Now, so again let's write the equation. So a into dou square 5 by dou x square plus b into dou square 5 by dou x dou y plus c into dou square phi by dou y square is equal to 0. So let's compare this one with this. So what is the value of A? A is equal to 1. So B is 0. C value is minus 2. Okay. Then what happens to the B square minus 4AC? So this will be equal to, so 0 square minus 4 into 1 into minus 2. So which will become plus 8. So therefore the b square minus 4ac value is greater than 0, and we can conclude that, so when x value is greater than 0, so what happens? The trigonometry equation has shown the characteristics of hyperbolic. Okay. Now let's see what happens. Again, the value of x equal to minus 2. Okay, let's see. So what happens? Fine. So when we'll see another slide. So when you have u of xx minus x of u of yy is equal to 0. So let us consider x is equal to minus 2. So what happens? U of xx plus 2 u of yy is equal to 0. Okay. So similarly, so what do we have? So dou square u by dou x square plus 2 into dou square u by dou y square is equal to 0. So again, let's write the equation here. So a of dou square phi by dou x square plus b of dou square phi by dou x dou y plus c into dou square phi by dou y square is equal to 0. Let's consider this. So here what happens? Let's compare these two equations. So when you compare these two, what happens? So the A value has turned out to be 1 and B value is turned to be 0 because there is no mixed derivative term, and the C value is plus 2. Okay. So when we get this, what is the value of discriminant? So B square minus 4AC. So what is the value of B? So 0. 0 square minus 4 into 1 into 2. So basically here it has come minus 8. So which shows that the b square minus 4ac value is less than 0. So this forms elliptic. Okay. So let's see what happens at x is equal to 0. Okay. So we have seen the positive values of x and we have seen the negative values of the x. So let's see what happens at x is equal to 0. So u of xx minus 0 into, so u of yy is equal to 0. So what happens? U of xx is equal to 0. So these are the equation which we have. So here what is the value of a? A is equal to 1, b is equal to 0, c is equal to 0. So therefore b square minus 4ac stand to be, so 0 square minus 4 into 1 into 0, which has come as 0. So therefore this will be parabolic. So trigonometry equation, so basically, so what happens trigonometry equation? So when the value of x changes, the behavior of the partial differential equation changes. So this is what we have in this equation. So here you can see trigonometry equation. So yeah, here we have, so u of xx minus x u of y is equal to 0. So basically it's a mixed elliptic and hyperbolic type. So when x values are x value is non-zero. So let's say when you use a is equal to 1, b is equal to 0, c is equal to minus x, so it has come as hyperbolic. But when you take x is equal to 0, it has come as parabolic. When x is negative, it will come as elliptic. Okay. So with respect to this, so when you see lambda 1, so when you see lambda 2, so we have one characteristic equation which is of root x and other characteristic equation which is of minus root x. So when you integrate, so these are the two characteristic equations. So between these two lines or the equations, so between these two equations, we have the changes of the fluid flow. Okay, so when we consider this as hyperbolic, right? So now let's see the pure hyperbolic equation. So what we have? So dou square u by dou t square minus c square into dou square u by dou x square is equal to 0. So this is one dimensional wave equation actually. So this one dimensional wave equation. So what happens? The a value has become 1. Okay, this is, let's consider a 1. So b value is 0. C value is minus c square. So what happens? So b square minus 4ac. So which has turned as b is equal to 0 minus 4 into a as 1 and the c value is minus c square. So which has come as 4c square, okay, which is greater than 0. So therefore what happens? The lambda 1 is c and lambda 2 is minus c. So lambda 1 is c, lambda 2 is minus c in the sense. So here we have, so dx by dt so is equal to c, dx by dt is equal to minus c. So when you integrate, so you have x is equal to ct into k1. So next equation, x is equal to minus ct into k2. Okay. So when you want to get the value of constant, we will apply some rules. Okay. But here you can see in the figure, so 1. So whatever the characteristic waves we have, so one has the negative slope, other one has the positive slope. Where, so what happens actually when you have the dx by dt positive slope, so and the negative slope, so this zone is called the affected zone. So these zones, whatever the region we have, so basically they are the unaffected zone for the case of hyperbolic equations. Okay. So with this, actually, we have seen some sample uh, examples for the hyperbolic, parabolic, and elliptic equations, and we have also seen basically the trigonometry equation. And there is one method, so where you can actually get into see, like get to know, so whether you have parabolic equation and the hyperbolic equation. So that is called the matrix method. So let's say you have certain equations. Okay. So let's take a1 x plus b1 y plus c1 is equal to 0. C1z is equal to 0. Okay. So this is what we have. So when you frame in terms of matrix, what happens actually? So this will be a1 0 comma 0. So this will be 0 b1 comma 0. So this will be 0 comma 0 c1 into x y and z is equal to 0. So by this method, so basically, so we call it as the eigen value method. So where here, if you see these eigen values, so we can actually determine, so whether it is parabolic, whether it is elliptic, or if all the values are zeros, so the diagonal values are zeros, so then you can say that it is parabolic. So where the data of a is will be is equal to 0. If data of a is equal to 0, so we can directly say as a parabolic, and if it is non-zero, so either it will be parabolic or it will be hyperbolic. So this is one more method. So where based on the matrix formation of matrix, we can determine, or based on the eigenvalues we can determine, so whether the equations what we have is hyperbolic or parabolic or elliptic. So having this knowledge, so what we have seen, so we have seen that the elliptic equation, so is the equation where it disturbs the flow field such that all the disturbances are propagated throughout the domain. Throughout the domain in the sense it will be moving everywhere. So there is no restriction or let's say there is no zone of restriction for the elliptic equation. So that is one thing. Whereas for the hyperbolic equation, so there is a restriction. So here we can see, so but from the hyperbolic equation, so this is one characteristic equation, and this one is the another characteristic equation, where in this equations, so we have the line equations. In between these two lines, so we have the disturbance, so which is propagated throughout a certain zone. So let's say if you extend this line in this way, so the disturbance is propagated in this way only. But if you come out of this, so what happens? This is called the zone of silence, let's say. Okay, so here this is the zone of disturbance. So which example we have related actually? So we have certain cases, so where we have taken Mach number, so which is less than 0.3, and in between, so in between 0.3 and this one, sorry, and we have Mach number in between 0.1.2 and 0.8, and we have Mach number in between 5 and 1.2. So we have Mach number greater than 5. So these are the zones which we saw. So let's say these zones are coming under elliptic equations. Why? So let's take an example. Let's take the airfoil. So when you have the flow as subsonic, so whatever the disturbance which you get here, it is propagated in the upstream in the sense in this direction, and it will be propagated in the downstream in this direction. Okay, so when the flow is subsonic, so let's say a Mach number less than 1, or let's say less than 0.8, so the mode of disturbance is propagated both up and downstream. But when you have the shock, okay, when you have shock wave, okay, so here the incoming flow, it sees like there is a thin layer, so which has changing a abrupt value. So whatever happens here, it does not affect this one actually. So it's the upstream thing is unaffected, and the downstream is affected. So for the hyperbolic case, so this is coming under this zone actually. Okay, so therefore when you consider this Mach number categorization or division, and when we categorize them with respect to elliptic and hyperbolic, so we say that so elliptic equation are majorly focusing on the subsonic or low speed regimes, where the disturbance is propagated everywhere, and when the hyperbolic equations, they are basically concentrating on the zone where the effects are happening. So the unaffected zone, it does not care actually. So this is the basic background of classification of partial differential equation, and the intuition or the equations methodology for the elliptic and parabolic and hyperbolic, and their significance and their application on the fluid flow phenomena. So this is what we have. So let's actually once see a momentum equation, so where we have so dou u by dou t plus dou by dou x of rho u dou x of rho uv, okay, is equal to minus dou p by dou x plus mu square dou square u by dou x square plus dou square u by dou y square plus rho g. So this is the 2D, two-dimensional momentum equation. Okay, two-dimensional momentum equation. So here what happens actually? So here you can see. So if you compare this, so this is of one form. Okay, so here this is elliptic. Okay, so you have elliptic nature and you have parabolic nature and hyperbolic nature in the combined momentum equation. So when you take only special case, let's say when you take only diffusion terms, this is elliptic. Okay, so when you take convection terms, basically they are like hyperbolic in nature actually. So this mixed combination is present in general equation, but when you are doing a CFD, so what happens, you will treat convection term separately and diffusion term separately, and the numerical methods applied for the convection terms and the numerical methods applied for the diffusion terms will be different actually. So when you take these things, so let's say only diffusion, so whatever the elliptic behavior is there, so what is the meaning actually? The diffusion is elliptic in nature. So diffusion in a sense, the spreading of the fluid flow. So when the fluid disturbance happens in the medium, so it will diffuse or it will spread throughout the domain. Okay, then this sort of problem is diffusion dominant. So when it is diffused in a certain zone or it is limited to certain zone, so we can say that so that has come to hyperbolic where the diffusion is less and the convection is dominant. So here on the left hand side we have convection, on the right hand side we have diffusion. Okay, so the balance of diffusion and the convection terms will happen for the momentum. So if the diffusion increases, the convection should decrease. If the convection increases, the diffusion is decreasing. So I think we can relate with the Reynolds number actually. So Reynolds number here we have, so which is rho VL by mu. So Reynolds number is nothing but the ratio of the inertial force to the viscous force. So the inertial force is relating to the convection and the viscous force are relating to the diffusion actually. So basically you can say it's a convection by diffusion. So if the Reynolds number is increasing, what happens actually? So the convection domination increases and the diffusion domination decreases. So if the Reynolds number is low Reynolds number, so let's say you have the bird flaps, okay, let's say any flow through any channels, let's say you have ventilation systems or you have the flow which is going through the industries, the smoke from outlets. So basically they are like low speed flows, so they can diffuse in the atmosphere with respect to time actually. So they form the vortices, so they break as they change their shape, they change their size as they go from one place to other place and form of eddies actually. So this thing happens actually in terms of convection and diffusion. So when flow or a smoke, let's say you consider, is going from one place to other place, it will move with help of convective force, and it will diffuse or it will spread with respect to diffusive force. Okay, so whatever the elliptic, parabolic and hyperbolic equations that we have learned, so we apply that concept in this momentum equation and the continuity equation and the energy equation. So that is why we have studied the mathematics of classification of partial differential equation, and we have seen in detail about the elliptic equation and the parabolic equation and the hyperbolic equation, such that when we see the governing equations, continuity, momentum and energy equation, so and when we are particularly solving only the diffusion terms or let's say only the convective terms or only special terms, so on which category they are falling. So let's say the diffusion term is falling under the category of elliptic, so we will follow that methodology to get the numerical schemes and solve those diffusion terms actually. So when you have the convection terms, we have hyperbolic equation. Basically, we will use those methodologies of numerical scheme such that we solve the convection terms. Okay, so when you combine, so the combination of convection and diffusion, you have other approach of numerical scheme. So this is what we have the background for the partial differential equations. So in the next class, so we will be seeing so what numerical schemes are especially used for the diffusion equation, and what numerical schemes which we use for the convection equation. So which order of accuracy is important, and when you combine convection and diffusion, what happens. So when you take separately, what happens. So we will see in detail. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.